Hi, Ray here, and I'd just like to read a passage I found very helpful from the intro to the book Program Logics for Certified Compilers, which is freely available from Princeton. Software is complex and prone to bugs. We would like to reason about the correctness of programs, and even to prove that the behavior of a program adheres to a formal specification. For this, we use program logics, rules for reasoning about the behavior of programs. But programs are large, and the reasoning rules are complex. What if there's a bug in our proof, in our application of the rules of the program logic? And how do we know that the program logic itself is sound, that when we conclude something using these rules, the program will really behave as we concluded? And once we have reasoned about a program, we compile it to machine code. What if there is a bug in the compiler? We achieve soundness by formally verifying our program logics, static analyzers, and compilers. We prove soundness theorems based on foundational specifications of the underlying hardware. We check all proofs by machine and connect the proofs together end to end so there are no gaps. Definitions. A program consists of instructions written in a programming language that direct a computer to perform a task. The behavior of a program, i.e. what happens when it executes, is specified by the operational semantics of the programming language. Some programming languages are machine languages that can directly execute on a computer. Others are source languages that require translation by a compiler before they can execute. A program logic is a set of formal rules for static reasoning about the behavior of a program. The word static implies that we do not actually execute the program in such reasoning. Hoare logic is an early and still very important program logic. Separation logic is a 21st century variant of Hoare logic that better accounts for pointer and array data structures. A compiler is correct with respect to the specification of the operational semantics of its source and target languages whenever a source program has a particular defined behavior, and when the compiler translates that program, then the target program has a corresponding behavior. The correspondence is part of the correctness specification of the compiler along with the two operational semantics. A compiler is proved correct if there is a formal proof that it meets this specification. Since the compiler is itself a program, this formal proof will typically be using the rules of a program logic for the implementation language of the compiler. Proofs in a logic or program logic can be written as derivation trees in which each node is the application of a rule of the system. The validity of a proof can be checked using a computer program. A machine-checked proof is one that has been checked in this way. Proof-checking programs can be quite small and simple, so one can reasonably hope to implement a proof checker free of bugs. It is inconvenient to construct derivation trees by hand. A proof assistant is a tool that combines a proof checker with a user interface that assists the human in building proofs. The proof assistant may also contain algorithms for proof automation, such as tactics and decision procedures. A certified compiler is one proved correct with a machine-checked proof. A certified program logic is one proved sound with a machine-checked proof. A certified program is one proved correct using a program logic with a machine-checked proof.